2 minus, hey, that's just x squared. So what we got? E to the 3x. Looks like the x squareds cancel, don't they? So x squared's gone. We got a minus x cubed. How many x's do we have? 4x. Constant terms. Plus 2, huh? Yeah. Anyway, it is possible I've made an arithmetic mistake in there, but this is how you calculate the Wronskian of a 3 by 3. So, theorem. Let's see here. The Wronskian of a solution set, if y1, y2, dot, 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 yn is solution set to, well, nth order linear ODE. All right. Then I need to come up with a name for this. Let's call it S. Then S is linearly independent if and only if there exists so that's still not saying it quite right. X naught in the domain of I need a solution set to an nth. The nth order linear ODE. Let's say that this differential equation is defined on the set. If there exists a point in U such that the Wronskian of y1 yn at that point x naught is not equal to 0. And I'm currently unhappy with my writing of this theorem, so let me just project it to make sure I don't have it misstated here. It's a little bit stronger than this. I mean, the funny thing is, there are examples of functions where the Wronskian is 0. It's possible to have a set of functions with Wronskian 0 and yet have the functions be linearly independent, which is annoying, right? Because I just proved that if the functions are linearly independent, then that implies that the Wronskian's non-zero, right? But you got to there are qualifiers that you got to be careful about. It's not an either-or thing. It's there's an exists and a for all floating about that we kind of ignore, and it'll get you into trouble. So if we have, come on, what's going on here? If we have not just a set of functions, but if we have a solution set, this is when the Wronskian is very intuitive. If the Wronskian's 0, the functions are linearly dependent. If the Wronskian's non-zero, the functions are linearly independent. So this is our primary application. We're interested in solution sets, so the Wronskian is useful. It doesn't deceive us when it's 0 for solution sets. Okay? Can you get me half the lights for me, Kang? Thanks. So, and this is a rather okay. Sure, why not? I mean, I'm probably going too fast for you to write this down anyway, so fair enough. So if we have an nth order linear ODE on an interval I, which just means a connected subset of real numbers, and we got solutions, y1 through yn. If there's even one point in I such that the Wronskian's non-zero, then they're linearly independent on I. On the other hand, if there is one point such that it's 0, then they're linearly dependent on I. Again, this is true for solution sets. That should be emphasized. Now, I'm going to show you the proof down here, and I put this on tests before, and students usually get it when I put it on the test because it's a really beautiful little calculation. You can all understand it. I encourage you to work through it. Take 5 minutes, work through this. It's important. I'll talk through it with you right now, but we can prove this in the n equals 2 case, and we discover something which is called Abel's formula, or Abel, if you like. So suppose you have two functions, all right? And suppose they solve a linear second order differential equation. So that means that we've got y1 and y2, and they solve a0 y prime prime plus a1 y prime plus a2 y equal to 0. And likewise, that's for y either being y1 or y2. Now, I'm no longer even assuming that a0, a1, and a2 are constants. They could be functions in this discussion. a1, a0, a2, they do not have to be constants in this theorem. So, you can calculate the Wronskian of y1 and y2. It's y1, y2 prime minus y2, y1 prime. Turn the lights for just a second. Thanks. And you might have to, did you move the camera up appropriately? Let me help you. It's here. There you go. So the Wronskian of y1 and y2 is the determinant of y1, y2, y1 prime, y2 prime, right? The determinant of that is y1, y2 prime minus y2, y1 prime, right? Now you can hit the lights again, King. So again, the Wronskian's y1, y2 prime minus y2, y1 prime. So what happens when you differentiate the Wronskian? Well, you get this mess, but two of the terms cancel because you got y1, y2 prime, and you also got a y1, y2 prime with a minus. But this is multiplication of real valued functions that commutes. So you're just left with these two second derivative terms. But second derivative terms can be converted to first and zeroth order terms by the differential equation because we're assuming y1 and y2 solve the differential equation. So that means that y2 prime, y1 prime prime is this, y2 prime prime is that, because again, we're assuming that you can plug them into the differential equation and it works. We're also assuming that this a sub 0 is non-zero on the interval. All right. Anyway, so you solve those, you plug it back into the w prime, and when you plug these in to there, something really cool happens. We get another cancellation. Let's see, the cancellation is like the y1, y2, right? And then there's y2, y1. So this piece and that piece. And it just leaves you with y1, y2 prime, y2, y1 prime, like this. But that's the Wronskian again. So what we've shown is that the derivative of the Wronskian is actually equal to minus a1 over a0, which could be functions, mind you, times w. But that is a differential equation we can solve, right? So that's dw dx is a1 over a0 w. We can solve that. That's separation of variables. And so you solve it, and that gives us the formula that w of x is c times the exponential of this. This is Abel's formula. This formula is beautiful. It's either 0 everywhere, or it's non-zero everywhere. It can't be 0 someplace and not 0 other places, right? Because this constant, right, if the constant's 0, the Wronskian's everywhere 0. If this constant is non-zero, the Wronskian's everywhere non-zero. So you either have linear independence or linear dependence, in fact. Like that. Now, you notice that this theorem is stated not for just the second order, but for the nth order, right? So to calculate the nth order, it hurts a little. But in fact, after some, well, tensor calculus, after a little calculation, you can in fact prove that the derivative of w is still minus a1 over a naught for w, even when there's n functions. What happens in the n equals 2 case happens in the n greater than or equal to 3 case, just the same. I don't require you to learn that. If you're interested and want to talk to me about it, I'm happy to talk to you about it, but I think that's kind of, it's a technical calculation, but I think it's important to say, because this Abel's formula is not just a second order thing, it's a always sort of thing, which is wonderful. We can always use the Wronskian to test for linear independence of solution sets. So that brings us to the definition. Fundamental solution set. What's a fundamental solution set? A fundamental solution set is a set of n functions that are linearly independent and solve L of y equal to 0. Okay? So here's the proof. The existence of a fundamental solution set. If I have L of y equals to f as an nth order linear differential equation with continuous coefficient functions on interval I, then there exists a fundamental solution set. So what you can do, this assumes there's a theorem that I have failed to project, but fine. There's those formulas for the determinant I was talking about. So if you go back to the start of this section, this is the sort of fundamental building block for all of our theory, which says that if you have an nth order linear differential equation and the leading coefficient is non-zero, which is to say it's really genuinely nth order, then if you have a set of initial data, there exists, in fact, a unique solution to the nth order linear differential equation. Okay? And then so we can solve an arbitrary initial value problem. So to prove the existence of a fundamental solution set, what you do is you just take initial data which make the Wronskian become the identity matrix. So going back over to here. Come on, where'd you go? Here it is. So because we have that fundamental existence and uniqueness theorem, we can solve initial data. We just solve the initial data mix, which makes the first one 1 and the rest of them 0, the derivative 1 and the rest of them 0, the acceleration 1 and the rest of them 0, and finally the n minus 1 derivative 1, the rest of them 0. When you calculate the Wronskian at that point, where we found all these initial data solutions, this Wronskian just becomes the identity matrix, which has determinant 1, which then shows you that these functions y1 through ym are everywhere linearly independent by what we just found with Abel's formula. So long story short, linear differential equations are nice. They have solution sets which exist and are linearly independent, which means we can build the solution as I've been showing you guys already for the constant coefficient case. So next time, and I'm sorry I didn't get to it today, I was planning to get to it, and I forgot to give you a quiz. Oh, we still got 2 minutes, right? What's that? 1 minute? Should I guess I can wait till next time for the quiz. I was going to give you guys a quiz today, but curses. So what's up next is I will try to actually, I don't think I ever actually defined nth order linear differential equation, did I? Did I? It's actually really simple. I wrote up the constant coefficient problem. The general problem is just this. It's the same thing. You just don't require the coefficients to be constants. That's a linear differential equation. That's it. So the thing we need to talk about next is, now that we have this idea of fundamental solution set, we know what linear independence is, the next chapter in the story for us is to deal with the non-homogeneous case. All right? So what happens when that g that I wrote up there, what happens when that's non-zero? How do we deal with that? How do we solve such problems? And it turns out the A we use today plays a prominent role. We do something called the method of annihilators. This is section 6.3. So I'll try to give you guys a quiz next time on how to construct solution sets to the constant coefficient problem. Yep. So thanks, guys.